Everything we do in linear algebra is going to require us to use matrices. And so in this first section, we want to build toward matrices and how to use matrices to solve systems of linear equations. So before we do that, I want to briefly review how we would have learned to solve systems of equations in the past using algebra. Specifically, we're going to be talking about how to solve a system of linear equations like this one using three methods: substitution, elimination, and graphing. And these are methods that we would have learned in an algebra class, maybe an Algebra 1 or an Algebra 2 class. And I want to review these because if we look at how to solve systems of linear equations using these methods, when we start solving systems using matrices, we'll be able to see that connection between solving with matrices and solving with one of these original methods. So in this particular video, we're going to be looking at linear systems like this one, a system of two equations and two unknowns. So we have two equations here, and we have two unknowns, x and y. We call this a linear system because both of the variables are linear. In other words, they're raised to an exponent or a power of 1, and we just don't write that 1 because it's understood. So this is really x to the first power. This is really y to the first power. And when that's the case, when all your variables are raised to the first power, it's a linear system. In other words, we don't have any x squared or y cubed or x to the fourth, anything like that, anywhere in our system. We have only first degree variables, so this is a system of linear equations or a linear system. And these are the kinds of systems that we're going to focus on in linear algebra. That's part of the reason we call it linear algebra, because we're dealing with linear systems. So let's look at how to solve this particular system using these three methods. We will get to the same solution for the system regardless of which method we use, and that's the point. We want to see how each of these three methods gets us to the same solution. So with the substitution method, our goal will be to solve one of the equations for one of the variables, and then substitute the value we get into the other equation. That's why we call it substitution. We can choose to start with either equation, and within that equation, we can solve for either variable. So our best bet is just to pick the variable that's easiest to solve for. In this particular system, there's not really one that stands out. Let's just go ahead and solve this first equation for the first variable. So we'll solve 6x plus 3y equals 27 for x. The way that we do that is by subtracting 3y from both sides. We'll get 6x. When we subtract 3y from both sides, it'll cancel it on the left, and we'll be left with 27 minus 3y on the right. Then we'll divide both sides by 6 to get x by itself. So we'll get x is equal to 27 over 6, which when we divide both the numerator and denominator by 3, will leave us with 9 over 2. And then we'll get minus 3y divided by 6, which again, when we divide both the numerator and denominator by 3, will leave us with minus y over 2. Now we've solved for a value of x, we can go ahead and make a substitution into the second equation. So we'll plug this value on the right in for x, and we'll get negative 5 multiplied by 9 halves minus y over 2 plus 2y is equal to 0. Now we have an equation that's in terms of y only, so we'll be able to solve for a value of y. If we distribute this 5 across everything inside the parentheses, we'll get negative 45 over 2. Negative times a negative gives us a positive 5y over 2 plus 2y is equal to 0. If we multiply through by 2, we'll get negative 45 plus 5y plus 4y is equal to 0. If we add 45 to both sides, that'll cancel the negative 45 over here, give us 45 on the right-hand side. 5y plus 4y is 9y, so we'll end up with 9y is equal to 45. Dividing both sides by 9 gives us y is equal to 5. Now that we have a value for y, we can take that value, plug it back into this equation we found earlier for x, and we'll find the corresponding value of x. So if we take y equals 5 and we plug it in here, we're going to get x is equal to 9 halves minus 5 halves. 9 halves minus 5 halves is 4 halves, and that's equal to x equals 2. And so we get an associated or corresponding value of x equals 2. So the solution to the system using substitution is xy equals 2, 5. And whenever you're solving using these methods, you want to go ahead and take the solution you found and plug it back into the equations to make sure that 2, 5 satisfies both equations. So if we plug in 2, 5, we get 6 times 2 is 12, 3 times 5 is 15, 12 plus 15 is 27, so that checks out. And then into the second equation, negative 5 times 2 is negative 10, 2 times 5 is positive 10, negative 10 plus 10 does give us 0, so that solution checks out. So that's the substitution method. The elimination method is where we use both equations at the same time and eliminate a variable. We can either subtract one equation from the other or add the two equations together and try to get one of the variables to cancel. But in order to do that, we're going to need to set up our system so that when we add or subtract the equations, the variable will cancel. So for instance, if I were to add the equations as is, I'd get 6x plus negative 5x. That would leave me with 1x. That wouldn't cancel out the x's from the system. Or for instance, if I were to subtract the second equation from the first one, I would get 3y minus 2y. That would leave me with a y. I'm not getting rid of the y. So we need to set up the equation so that one of the variables will disappear. For instance, one way we could do that is by multiplying through the first equation by 2 to give us 6y here, and multiplying through the second equation by 3 to give us 6y here. That way, if I have 6y in both equations, I can subtract one equation from the other and the y's will actually cancel. You can choose to eliminate either variable. We can try to eliminate y or eliminate x. It doesn't matter, it'll work both ways. You just want to pick a variable that seems fairly easy to eliminate. So let's go ahead and multiply through the first equation by 2. When we do that, we'll get 12x plus 6y is equal to 54. And if we multiply through the second equation by 3, we'll get negative 15x plus 6y is equal to 0. Now elimination tells us that we can go ahead and subtract the second equation from the first. So we'll subtract, we'll put parentheses around the second equation to make sure that we distribute this negative sign across all of the terms inside the second equation. So here we'll get 12x minus a negative 15x. Those negative signs will cancel and become a positive sign. So it'll be 12x plus 15x is 27x. 6y minus 6y will give us 0, so that'll disappear. And then here we'll get 54 minus 0 is a 54. If we divide both sides by 27, we get x is equal to 2. So we found a value of x. Now we need to take that value and plug it back into either of these equations or either of the original equations to solve for the corresponding value of y. Let's go ahead and plug it back into this second equation here for no particular reason. Let's just pick that one. So we'll get negative 5 times 2 when we plug x equals 2 in here, plus 2y is equal to 0. That gives us negative 10 plus 2y equals 0. Adding 10 to both sides, we get 2y is equal to 10, and dividing both sides by 2, we get y is equal to 5. So the corresponding value of y is y equals 5, and you can see here that with elimination, we found the same solution, xy is equal to 2, 5. And again, if we were just doing elimination, we would want to make sure we plugged 2, 5 back into the original system, but we've already double-checked it when we did the substitution method. And then the final method that we want to use is graphing. And a simple way to graph any linear equation is to put it in slope-intercept form, which means that we'll solve it for y. So let's take this first equation, 6x plus 3y equals 27. Let's subtract 6x from both sides. So when we do that, we'll get 3y is equal to negative 6x plus 27. We want to get y by itself, so when we divide both sides by 3, we get y is equal to negative 6 over 3 is negative 2, so negative 2x, and 27 over 3 is 9, so negative 2x plus 9. Let's go ahead and do the same thing with the second equation. If we add 5x to both sides, we'll get 2y is equal to 5x plus 0. There's no reason to write the plus 0. And then if we go ahead and divide both sides by 2, we get y is equal to 5 halves x. Now we have both equations in slope-intercept form, which means that they'll be easy to graph. So let's go ahead and graph each one of them. For y equals negative 2x plus 9, 9 is going to be the y-intercept, or the point at which the line intercepts the y-axis. So we come up here to 9, and we can plot a point along the y-axis. And then the coefficient here in front of the x gives us the slope of the line. So since the slope is negative 2, that tells us to go down 2 and over positive 1, down 2 and over positive 1. And so if we've done this correctly, our graph should look something like this when we sketch it. This will be the graph here of y equals negative 2x plus 9. And then if we sketch the other line, y equals 5/2 x, remember we have an implied plus 0 here, which means the y-intercept is at 0. And then from there, our slope is 5/2, which means we go up positive 5 and over positive 2. And that gets us to about this point here. We could go up another positive 5 and over another positive 2, and that might get us to about here. Then if we've done that correctly, our line should look something like this. And we can sketch that in, and that's the line y equals 5/2 x. And then to determine the solution with the graphing method, we look at the point at which the lines intersect one another, which we can see is this point here. And if we can tell from the graph, that is the point xy is equal to 2, 5, the same solution that we got using the elimination method and the substitution method. So as we move forward and learn how to use matrices to solve systems, keep these three methods in mind and just realize that solving the system using a matrix is doing the same thing as solving the system in one of these three original ways, but using a matrix is going to turn out to be much, much easier, especially as the linear system gets larger and larger with more equations and more unknowns.